All right, hey, looks like I am live, and let me tell you, I think I am in trouble because I looked at today's problem to get the link for this stream, and it looks really hard. uh, like, so hard that it's actually marked as a hard on LeetCode. So, today is the last day of the challenge for May. It says it's completed, but it's not. If we go in here, you see I've got one more problem. And I knew just reading the description, given two words, find the minimum number of operations required to convert word 1 to word 2. When I read that, I knew that we were looking at a diffing algorithm. And I know that diffing algorithms are like notoriously difficult, and I don't think I've ever done a diff problem before. I don't think I've ever even attempted it. So the chances of me figuring this out in a reasonable amount of time are low. However, I do want to give it a try and kind of think about the problem a little bit before going and searching for an algorithm that's going to do this. Hey, what's up, Vic? Let me fix the chat. Long time no see. Hope you're doing well, eating lots of ice cream. Fix. One of these days, I'm going to fix my setup completely. There we go. Yeah, so this problem, notoriously difficult. We have three operations that we can do on a word. We can insert a character, delete a character, or replace a character. So in the example here, we got horse. And we need to make the word ROS. So, you know, as a human, I can see that we've got the same letters. I didn't say anything about moving a character. We can replace a character. But I don't want to look at their explanation yet. Just trying to think, like, as a human, how would I do this? I mean, I would see the R and the S, and I would think maybe just inserting an O. Oh, but we can't oh yeah, we can insert. So we insert an O, and then we delete these three. But that's 4 steps, so we can actually do this better. We just replace this with an R, and then drop these two through 3 steps. Okay, so so maybe as a human, I could come up with some sort of procedural way of going through everything, and we can figure out how to optimize that. Hey, that's my switch code. If you want to add me on Switch. Let's see. There we go. So if we add horse, I know there's no H. So what I can do with that H is I can delete it. I can insert. I don't even know how to deal with insert. I mean, I can insert some character. Oh my gosh. Or I can replace it with some character. Ah, man, that's tough. Like, I thought maybe I could kind of iterate and just try all the combinations, but even this, like, deleting is easy. But insert some character. Which one? The first one would be the first one I would try. And then I need some way of judging whether I got closer or further to my goal. So maybe if I had some way of, like, scoring the word. Like if I compared the words now, and by the way, I don't have to return the word or what the replacements were. I just have to return the number. I doubt there's some easy mathematical way to do this, but it's worth a shot. So if I look at this rows, I can see that I've got 3 of the same letters. They're in a different order as here. So just based off that alone, it doesn't tell me anything. Let's see, how to score. Same letters in same order. So here I can see that either if I go RS, O, or OS, then I can get like a 2. So I can say that there's 2 letters in common in the right order. So from there, I know that I can delete or replace 3 times. Oh, this is hard. Ooh. Jeez. So what would be my score here? It'd be something like oh jeez. Look for the bigger word and start looping. Check if word I equals word J. If not, yeah, let's see what that looks like. All right, so look for the bigger word. All right, we're trying to make horse into rose and not rose into horse. Although that, I mean, either way, it's kind of the same, right? Like, maybe. It's an interesting way to think about it. Look for the bigger word, start looping, check if the word and I equals the word to and I. So does H equal R? If not, then set word to equal to word 1 and I. So here, for example, I would increment my count of changes and say, hey, boom. So now we're good. We advance to the next letter. It's the same. We advance to the next letter. It's not the same. So would I delete or replace? And does it even matter? What's the difference? So I made one change to swap the H with a R. So I've got the R and the S. I should delete, and that would be good. But I can only delete because I know that the next letter is later in my list. So 2 to delete it, and then 3 to delete that. So I had to look ahead to see if a swap or delete was better. Let's try this with the second example, intention and execution. And we need to make intention into execution in the least number of steps. Repeat the same process for both words. Find out which count was less. Oh, that's interesting. Okay, yeah, let's try that. So here, I've got an I and an E. And if I look forward, I can see there's another E. So I'm either swapping this with an E, or I have to go up to this E. Ooh, how do I know which way is better? I could try them both. So I could say, hey, we got 2 paths. Swap I for E, or delete up to E. Oh, this is just too much. So what are the ideas we kind of talked about? We talked about doing a, let's see, like a character by character replacement, and choosing the best answer, basically. The best answer that we can get, which means doing some sort of like forking on decisions, either by look ahead or some other way. Another way to kind of a variant similar is to basically score each iteration on if we're getting closer or farther. Closer or farther? That word looks weird now. Farther. I mean, I've seen ones where you have to delete letters in order to make them, and those weren't too bad. And we kind of did something where we would go through, we would try deleting. It would basically be like a kind of dynamic solution. But these other two options are really crazy to me. So I don't really know how to approach, and I think that I'm not going to get there in a reasonable amount of time. So I'm going to ask the internet about diff algorithms. And let's just start here. There are several diff algorithms. The idea is to find a modification script that will turn text A into text B. You use modification operations such as insert and delete. Okay. Usually you want the minimal number of changes required, but sometimes you have to weigh the operations depending on which is more desirable. With a bit of further modern literature, these comprehensive papers are easy to find. I don't want to read a paper. 1978. I kind of feel like if I have to read like a several page paper about a problem, that it's definitely hard. Some more recent diff style algorithms: X delta, rsync, BS diff. I've never heard of any of these algorithms. Hunt McElroy is considerably faster for line-to-line comparisons. We just have a word-to-word. Huh. Amino acid sequences. CVS program the basic algorithm. So this is good background info. I'm not really finding any like good clues for where to look next. Oh, here we go. The core of the diff algorithm seeks to compare two sequences and discover how the first can be transformed into the second by a sequence of operations using primitives like delete and insert. We don't have a replace. A replace is not much different than a delete and an insert. We just have to, like, if we see both of these combined, we have to not count it twice. Maybe that's not a bad modification. Oh, here we go. Yeah, if a delete and an insert coincide on the same range, it can be labeled as a change subsequence. User doesn't always want to be informed as to which subsequences remain identical. Blah, blah. Is there a possibility that turning a smaller word into a bigger word will take less steps? That's a good question. So if we look at, let me keep that. Horse and Roz. So here we 1, 2, 3, 4, but that's not necessarily the best way to do it. Is there a way for us to do this with 3? 1, 2, 3. Yeah, so I was able to do it the same with that example. I don't know. What's another one? Racer and Acri F. Take the shorter word and try to make it into this. So I don't know. Well, this isn't a good way to figure it out because I don't know what the optimum number is. So, geez, I just don't know. Quick diff. Read a little bit more. The sophisticated way to find those editing operations is to sort the two sequences in order of the values of the elements of the sequences. For when the basic unit is a text line, usually a hash code of each line is used to represent the line, and the sequences are sorted by a hash code in order to discover groups of identical elements or lines. Once identical elements are found, they are clumped together into runs, which were adjacent in the pre-sorted sequences. So this is nice for lines. I don't know if it's going to help us for words. But if we look at that horse and Roz example, here, if we kind of score subsequent runs, we could see Okay, there's a run of 5. So imagine we gave it a value of like, something, some sort of hash code to represent that. And Roz has a run of 3 at 12. Then we could look at a sequence of 4 whores and give it, some other kind of score. And then we could look at 3. And so we have to do all the permutations, which is computationally horrifying. So in this case, there are no 2 runs. So here we have to do all that work only to say we don't have any runs in common. So let's see what they say to do next. Once identical elements are found, they are clumped together into runs which were adjacent in the pre-sorted sequences. One common variant looks for the longest possible of such runs, which is n squared, which is scary. But for n equal to the number of possibilities in each group, not the number of total elements. Okay, so the diff is dependent on the number of differences, not the size of the input. This is usually acceptably fast enough. At this stage, all matching regions between the 2 sequences and files have been found. Running sequentially through the elements lines that have not been matched now trivially indicates which regions have been inserted, deleted, or changed. Usually moved regions are indicated as an insert and a delete, but with some extra effort. They can be reported as moved. Yeah, there's protests downtown Orlando, shut down some of the highways. I haven't really been keeping up with the news though, so I don't really know what's going on. I should probably find out. I live in a pretty kind of rural area of Orlando, so it's not. I don't expect to see anything crazy going on. I don't really know. I don't really keep up too much with the news, so I'm not really too up on what's going on in the first place. Which probably should be. Oh, I like this one. The smallest versions of the algorithm can be implemented in less space than the above text of this article. It's less complicated than it may sound. Okay. Oh, this is talking about kind of looking for plagiarism or kind of scoring 2 to. I mean, that could be good though. 2 strings are mostly different, but share a small, common, or nearly common part or parts. The individual parts are usually in blocks or groups with only small segments changed. To add to the larger blocks of similar text may not be in the same order, but shuffled in sequence. This sounds a lot like what we've got here. And it is when that happens that the normal diff algorithm breaks down. Diff is designed to compare things that are mostly the same with small amounts of modifications. And we don't know that we have that. And what can you do to deal with strings that have been shuffled or which are mostly different? We've got some notes, but it's getting kind of weird and rambly. I don't really know. So I guess these are people's comments. Let's try another page. What about Meyers Diff? Ugh, I don't want to read all this. The smallest number of changes in A to produce B. That's what I want. Okay, I'm going to have to read diffs, blah, blah. Okay, that's why diffs are great. They're important. Think for a moment how you'd calculate diff. I didn't get very far. And how you'd write a function to do it. You might have noticed that diff programs only show you what have changed, not what has stayed the same. How would you determine which parts of a file have not changed? Once you found a difference between them, how would you find the next line where text matches up? Oh man, this is a series of articles. What up, Matt Wolf? Wouldn't it come down to the max number of in order car in words one? Yeah, that's what I was kind of wondering about, kind of scoring. Since replace, delete, and insert all score the same. Yeah, I wondered if there was like a mathematical way to just kind of figure out like, hey, this has 6 characters and this is the ordering of it. So that's 3. 6 minus 3 is 3, done. So that makes sense to me that we should be able to figure that out based on the number of items the same. We have an example of horse and Roz. So we know that the greatest number of in sequence letters between the two is 2 for either OS or RS, either one. So I do have 5. So is it enough to just say 5 minus 2 equals 3? It's the right answer. Let's try this other example they gave us where we should get the word 5 or the result 5 for intention and execution. Whoa. So this is even kind of hard to figure out. It's like the longest common subsequence. That's probably a famous algorithm by itself. There's no I. There is an N, but it's near the end. There's no T. We do have an E. That looks like it's probably good. We do have an N. The E's better to keep, so the answer is 5 here. Because we have the E for execution, and then we have the TION. And the total number of letters in the bigger one is 9. So if we did this math, then we would think that the answer would be 4. But the answer is 5. So not really sure what to do with it, and even figuring out like the correct order of things is tough. Yeah. Let's see, default diff algorithm used by Git. It's the Meyers. So this is nice. We get 2 sample words, and we're talking about doing a diff on them to come up with a sequence of edits that will convert A to B. One possible such sequence is simply to delete each character and then insert B, or to use the common diff. Okay, however, that's not good enough. We want to see changes like this. Okay, this makes the smallest number of changes to an A in order to produce B. So it's a better visualization of what really changed. It's not the only possible solution, but there are others. However, they are all minimal. Okay. So the purpose of diff algorithms is to provide a strategy for generating diffs, which are as small as possible. Oh my gosh. Meyers algorithm is just one strategy. It's fast, it produces diffs that tend to be of good quality most of the time. It's greedy. Ooh. Is based on the idea that finding the shortest edit script can be modeled as a graph search. Let's take our 2 strings, ABC, ABBA, and CBA, BAC, and build a graph of all the ways we can get from A to B. So that's similar to one of the approaches we talked about. Okay. Moving. Okay, wow. This is really complicated. The XY coordinates in the grid shown below correspond to steps in the editing process. At 0, 0, we have string A. We have not started editing. Moving rightward corresponds to deleting. Moving downward corresponds to inserting. Okay, as well as moving rightward and downward. In some positions, we can also move diagonally. This occurs when two strings have the same character at the positions indexes. For example, the third character in A and the first character in B. So position 2, 0 has the diagonal leading to 3, 1. This corresponds to consuming an equal character from both strings. So basically keeping it. The idea behind this is quite simple. Oh. We want to get from 0, 0 to 7, 6. So basically the top left corner to the bottom right corner in as few moves as possible. Oh, this is pretty cool. Okay, and we've got like a little map of things we can do. Okay, wow. A move is this. Oh, this is cool. Okay, a move is a single step rightward, a delete from A or downward, and insert B. The most number of moves we could take to get from A to B is 13. Combined length of the two strings. So that's the worst combination would be basically deleting everything and re-adding. However, walking diagonals is free since they don't correspond to making changes. So we can maximize the number of diagonal steps. The examples above show that we can actually get from A to B making only 5 edits. How do we do that? So we're starting here, and here we have to go either right or down. So I'm just going to say we go right first. So we go right first. Here, same deal. We go right or down. So we go right. Now here we've got a diagonal, so we take it. Diagonals are always better because they move us both right and down at the same time. So now we're here, same deal, right or down. We'll go right. We've got a diagonal, always take it. Okay, right or down, right. Diagonal, we always take it. Okay, and the rest are downs. So that took us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hops. There's probably a better way to go. So if you want, I'll try going down every time. So 1 hop, 2 hops, 3 hops, 4 hops, 5 hops, 6 hops, 7, 8, 9, 10. So I actually did a little bit worse going just down. But what I really want to do is just keep trying. It's basically like an A-star algorithm at this point. So we can keep trying. And if we ever exceed the minimum number of hops we've seen so far, we can just stop and try a different path. So path finding isn't too bad. So basically what we got to do is build a graph that maps what links to what, and then we can do like a traversal algorithm, either BFS or DFS, in order to work through all the various paths we can take to get to this in the minimum number of steps. So, phew, that's a cool way of thinking about it. Now, I don't quite understand how to generate this graph. Did they explain that? The XY coordinates in the grid shown below correspond to steps in the editing process. At 0, 0, we have string A. Okay, moving rightward. Okay, I understand the movement. How do I figure out the graph? Build a graph of all the ways we can get from A to B. Changes. Okay, develop an intuition. Let's start by exploring the graph. So I get the graph. That makes sense to me. Once I get the graph, I know what to do. We iterate like a A-star algorithm and find the shortest path. It's based on. Okay, and next algorithm, or next article, Anyway, thanks, James Coughlin. Yeah, keep an eye on what else he's got on this blog. This is good stuff. Building Git. So in part 1, we saw how the two diffs is modeled as a graph search. Okay, and here's an example. Whoa, that's cool. Now, having seen how the graph search works, we're going to change the representation slightly to get us towards how the Meyers algorithm actually works. Oh boy, but I liked it like that. Looks like basically the same thing, they just flipped it on its head. So they kind of rotated it 45 degrees. Okay, yeah, 45 degrees. The number along the horizontal, whoa, whoa. The number along the horizontal axis D is the depth we've reached in our graph. Okay, so I see that, yeah. 0, 0, 1, 2, 3, 4, 5. Okay. Moving rightward increases x, and so increases k by 1. Well, I gotta reread that part. Horizontal is the depth we've reached in the graph. How many moves we've made so far. Okay, remembering that diagonal moves are free. Okay. Looking at it this way makes it kind of hard to see where the diagonals are. The number along the vertical axis is k, and notice how for every move in the graph, k equals x minus 1. What? For each move on that row. What? X minus 1 for the row. Numbers along the vertical we call k, and notice that for every move in the graph, k, which is the vertical, is equal to x minus y for each move on that row. So we're saying 0 equals x, which is 0, minus y. Oh, x minus y. So 0 minus 0, 2 minus 2. Okay, so it's the difference in x and y. So here it's x minus y is negative 1, negative 1. Wow. Whew. Okay. 7 minus 3 is 4. Okay, so here's how the algorithm proceeds. For each D, we fill in each move. Oh my gosh, this is painful. I thought the algorithm we'd end up would be kind of easy. I'm just going to skip ahead and look at this code. We can translate this into working code. We create a function that takes two lists, which will contain diff line objects that represent lines in a file. Our diff code will mostly only rely on the text field of these objects, but it's useful to store the original line numbers, which I don't care about, for printing. Okay, I'm getting lost in the details. I think I'm just going to keep an eye. I'm going to keep that open for that book, and then Meyers Diff. The basic greedy algorithm. I have a hard time thinking of this as being basic. Like, here's the table of contents. Ugh. Shortest edit script. This algorithm finds the shortest edit script that converts A to B. SES contains only two types of commands, deletes and inserts. Okay. Finding the SES. Oh, this is interesting. Finding the shortest edit script is equivalent to finding the longest common subsequence of the two files. You called it, Mike. Sorry, Matt. Matt Wolf. Finding the longest common subsequence of the two files. LCS is the longest list of characters that can be generated from both files by removing some characters. LCS is distinct from the longest common substring, which has to be contiguous. So yeah, so when we looked at intention execution, so here I said the longest common substring was 5, and we tried to do some math on it in order to get the right answer. And like we said, it's kind of tough to figure out the longest common substring. Okay. For any two files, there can be multiple LCS, and it doesn't matter. Sample sequences. Hey, cool. Someone wrote an app. It'd be cool to make a little web app doing this, showing this. This is the edit graph for the example. Array A is put along the x-axis at the top. Array B. So this I understand. When I see this graph, like, I get it. We count the number of hops. How do we get that graph for horse and Roz? Okay, snakes. A snake is defined as a single deletion or insert followed by 0 or more diagonals. What? Snake. For example, there are two snakes starting at the top left. One goes right and stops. Boom, boom. Single deletion or insertion followed by 0 or more diagonals. 0 or more diagonals. The next snake goes from... Oh, there are two snakes starting at the top left. Okay. One here, that's one snake, and then there's the two snake that ends in a diagonal. Okay. Whew. Oh my god, I hate this so much. Yeah, it looks daunting, for sure. Okay, I mean, I kind of get this. I don't understand why it's not sufficient just to count. I guess maybe for our algorithm, we just need to return the number. So it's probably okay just to count the hops, but I don't quite understand the scoring yet. Oh, okay, I think I get it. So this helps us kind of determine. So this is kind of what we talked about, basically. So the second solution we talked about was basically scoring to see if we're getting closer or farther. So this helps us determine whether we're on the right track or not. So we don't have to do as much work in the graph. Whew, okay. Meyers Diff. Oh, we got a visualization here. We got an algorithm. My god, look at this monster. By the way, I should say, Meyers, when Meyers came up with this algorithm, probably spent a whole lot of time thinking about it. Okay, cool. So this is showing us how to construct that graph. Empty snake, add insertion, empty snake. Follow the snake. Wow, what on earth is going on here? So form a grid using the two strings. Okay, I understand this. Okay. This makes sense to me. So up here we'll have horse, down here we'll have raws. We can label each of the points. Okay, fine. The first step is easy to understand and involves laying out a grid that allows us to compare different subsections of the two sequences we want to compare. So, oh, I see. Okay, so here we have a C and we have a C. So it lets us draw a diagonal. Oh, the B and B lets us draw a diagonal. B and B, diagonal, B and B, diagonal. So those are all potential places for the longest substring. So, given that, let's try it with horse and Roz. So horse up top. And Roz down below. So here, we get a diagonal here. We get a diagonal here. S, we get a diagonal there. So we start at 0, 0. This is hard to see. What's a better way of doing this? Excel. Let's see here. I have Excel. All right, so here we have horse. And Roz. Thank you, Microsoft. So let's put a border or something. Okay, I don't know how to use Excel anymore. There we go. So for the diagonals, I'll just put a slash in there. Okay. Now we start at the top left, 0, 0. And we either go right or down. So we have a minimum of 1. If we go right, then we can take a diagonal. Okay. Diagonals are free. So that leaves us at the intersection here of R and O. Now you can either go right or down, which will be 2. That's not what I expected. So here I either go right or down. I go, oh, okay, yeah. I didn't count enough. All right, let's try this again. So from here, the tip of R and H, we go over 1. That's not a formula. Oh my gosh. We go over 1 to the right. And now we're actually up here in the top right. We're at this position, so we have to go down. So to get out of this square, we have to do 2 moves. Then diagonal's free. And now we're at the intersection of O and R. So we do 1 more to go to the right. And we're good. So let's try intentional and whatever the other word was. What are the chances of me spelling this correctly? Very slim. Yeah, it might just be easier to do this in code. In IntelliJ for sure. All right, we'll call this one Meyers This is ultimately what we have to fulfill. I'm going to make another function though called generate graph, and we'll take in word 1 and word 2. And what does the data structure look like in there? We have to store. The diagonals are always one way or the other. So it's basically true or false. Either it has a diagonal or it doesn't. So we can do that with a matrix, an array of booleans. Okay, boolean. And the size will be, we'll just say word 1. But it's not just an array of boolean, it's an array of booleans. Okay. The length is word 1. We have to initialize it. Is that right? Required int to negate. Oh, it's dot size. Dot length. Okay. There's one array. To initialize it for each item, we'll have an array of booleans that are the length of word 2. What's the problem here? Oh, geez, same thing, dot length. Okay, what's the problem? Oh, and I need to initialize it to false. Okay. Then word 1 dot for each. We'll say it's character 1. Word 2 for each. I need index though for each indexed. For each indexed. I2 and C2. What are we doing here? Basically, if C1 equals C2, if we have a match, then result at I1 for word 1 and I2 for word 2 equals true. It has a diagonal. Okay. Result. Which is an array of booleans. All right, so we got our graph. So let's write a test function. I lost my class, my inner class. All right, so down here we got a test. It's going to be super fun. And we'll start with horse and Roz because we know what that should look like. Result equals generate graph. For horse and Roz. And just like I said, Vic, I don't think it matters which one's word 1 or word 2, whether you're going from the bigger word to the smaller word or vice versa. think it's the same. So great call on that. Now, for my asserts, I think I can basically say result at what should be what. O is in the same position, so that's 1. At 1 should be true. Also, the R, which is in position 2 in word 1 and 0 in position in word 2. And then finally the S, which is in 0, 1, 2, 3, and 2. And the rest should be false. So maybe I could do assert equals result dot count. I don't want to do that. I don't want to program a bunch of, I don't want to complicate a test. I'll probably regret that, but hey. Okay, we've got an error, expected value to be true. I got a false. So what happened? Everything's false. Okay, how did that happen? We went through every word in one. Oh, I got an extra bracket here. Let's try this again. I'm not sure why that wasn't an error. I think it maybe just is, that's funny. Yeah, so it just like created a block of code that wasn't ever getting executed. Loop through each one and created the code. Done. Alright, so that's good. We'll double check it to make sure that the rest are false just by hand. I guess probably fine. Alright, false, 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 true, false. True, false, 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 true, and it should be all falses. Yep, we good. So I think this algorithm is probably fine. Let's try it for indentation and whatever the other one was. So let's see, example 2. Alright, intention and execution. So we counted this up. How many trues should there be? We said the greatest subsequence was 5, but I don't know. Yeah, I'm not going to try and do this by hand. That's too much. What about EDF and EEE? In this case, we should get 3 1s. They should be like 0, 0, 0, 1, 0, 1, 2. Do that right? Yep. The rest should be false. Alright, I think that's sufficient. Say that this algorithm is good. So that part was easy. Now we can find out min distance. Get our graph. Hey, what's up, Abdul? So, TION is the subsequence. Yep, I think that's the longest a contiguous subsequence. So the deal with the graph Abdul is that I cheated and looked up diff algorithms, and I found one called the Meyers Diff Algorithm, which is apparently really common. And so, like, if you look at this graph here, basically we got word 1 up top, word 2 to the left, going down. And what they did is they counted what they called a diagonal, which means you can do which means that the letters are in common. So C and C gives us a diagonal, B and B. And what that means is that we can use those paths to cheat and not count them. So what we're trying to do then is basically find the optimum path from 0, 0, which is the beginning of both strings, to basically whatever is, oh, I can click through it to do it, that's cool, to get through it. And so basically at this point, now that we have this graph, what we can do is start here and just do a standard traversal. So there are better algorithms. It looks like gets this algorithm that goes kind of nuts in order to figure out the fastest way to move through this. But I think for this problem, it might be sufficient just to do like a standard traversal and find the minimum path between these things, with the caveat that we don't count any diagonals. So diagonals are great because those letters are ones in common, so we don't have to change anything. So this example is too long. Oh, I can make my own. Cool. So if we do horse and Roz, then there's what it looks like. So I start here, I go to the right, that's 1 hop, go down 2 hops, diagonal 3, 3 hops, go to the right. Oh wait, I didn't mean to count that, so sorry. Let me start over again. Here to there is 1, down is 2, diagonal is free because it's already the same. Now moving to the right is 3, down diagonal is free, and then moving to the right is 4. Now the right answer here is 3 because we have replacements. So in addition to, or rather as we're counting, whenever I see us do a delete, which is moving to the right, and an insert, which is moving down, then I can collapse those into a replace. So here where I went to the right and then down for H, we can replace that with a replacement instead of a single insert. So I basically have to just kind of watch out for that condition. But other than that, I think it's just a straightforward shortest path algorithm like an A*. Not that I know how to do A* offhand. So I think I can probably figure that out. Or I could just kind of cheap out and try to do just a brute force kind of thing. So, yeah, I don't know. Let's look up A* algorithm and see. Yeah, and like you said, I saw this problem was a hard. I was like, oh boy. So I started Googling diff algorithms. All right, see, do we have a simple description, pseudocode? This does not look simple. Total path. And we don't actually need to store the path. We just need to keep the cheapest, return the cheapest one. Oh geez, this looks complicated. I think I might just kind of do it my own way, which is probably a terrible idea. Basically, it looks like it's just getting a score, and so if it sees that the score goes worse than the best score we've seen so far, then we don't have to continue. Because we know it's only going to get worse. So here, we'll do a traversal. And I'll write that as a separate function. Minimum traversal. Minimum steps. We'll take in a graph of booleans. And don't let me forget about replace. Remember, delete plus insert together. Collapse to a replace. Okay. A two-liner? Oh my gosh. That's ridiculous. Well, if this ends up going too long, maybe I'll look for that. I'm already an hour in, and that's with cheating. But the cool thing is, I mean, I learned about Meyers algorithm, and I guess Git uses that by default, which is pretty cool. So I got to learn a little bit. Call this graph. So we start at 0, 0. So maybe current position. How do we want to do this? Do we want to do it recursively or iteratively? Let's just do it iteratively. What's the easiest way to do that? What is the easiest way to do that? Well, first we need to keep track of our least steps. Set it to infinity, or rather int dot max. Okay. Why is that white? I thought I used that. All right. So here, standard traversal. Trying to think the best way to do this, DFS or BFS for a graph. Let's just do BFS. No, I think DFS will be better, which means we need a stack of what's. The stack should have, I think we just do a pair of int, which will be like our X and our Y. We also have tracked visited, don't we? Visited equals a hash map of pairs of int. Whoa, oh, hash set rather. Okay. That's probably going to want me to do a mutable map of. I'm fine with that. And let me guess, stack is an interface. No, okay. I need parentheses. All right, cool. So, stack.add our first item, which is going to be pair of 0, 0. Oh yeah, it's kind of weird to iterate through this way, because I can't, like, I don't have like easy way to get neighbors, but whatever, it'll work. While stack dot length. I'm already regretting not looking at that A-star algorithm better. And with a matrix like this, stack dot any. Yeah, there's better ways to do shortest path. Hold on here. We don't need a stack. We don't need no stinking visited. I think it's Dijkstra's algorithm. Dijkstra. And if I remember correctly, it's basically 3 loops. I'm sure I don't remember it correctly. There's also Bellman-Ford. Or Bellman-Ford. So I'll spend a few minutes trying to kind of figure it out on my own. But we're already an hour in, so if I don't figure out something good here in like 5 minutes, I'm gonna go look up one of those. For val I in graph dot indices, graph dot size. Whatever. We could say the same thing as graph dot indices. Oh, come on. Indices, there we go. We don't need the val, it's implied. Okay, for j in graph dot graph 0 dot indices, so this will be word 2. We should name these C1 and C2. Character 1 and character 2. Oh no, I don't. These are actually the indices. So I'm missing a loop here. We're going across all the i's and all the j's and what? Alright, I'm looking it up. Shortest path algorithm. Let the node at which you are starting be called the initial node. Let the distance of node y be the distance from initial node y. They're doing a BFS. I thought DFS would be better here. Whatever. Mark all nodes as unvisited. I'm just going to copy this and I thought it was just a triple for loop. Here's some pseudo code. Let's try Bellman Ford. Shortest path from a single source to all other vertices, which I don't need. I just need to one specific one. This might have been what I was thinking of where, well, no, there's more than, yeah, I don't know what I'm thinking. So what's the difference between Dijkstra's and shortest path algorithm for finding the shortest path between nodes? I don't need to. We can just do A star. A star is going to be the best. Generated nodes in memory. That's fine. Best first. Okay. Blah, blah, blah. Following pseudocode. Oh my gosh. So, first, total path equals current. I don't want to read no stinking Python. Alright, I'm getting lazy now. Let's find like a star simpler implementation. Okay, this is what we want. We've got a nice matrix. We've got some diagonals. All right. Algorithm. Just going to copy this in and just transcribe. Line by line. This is about as cheaty as you can get. I like it. Oh, hey, sorry, I didn't see the comment. What's up, Adagali? Meyers is the same as the DP idea. The reason you only need DP here is because there's only a need of count of steps. Okay. Meyers will give you the actual sequence of steps. Okay. Okay. Yeah, so that makes sense. So I guess you... I don't know. Still... I don't know. My brain is kind of melted from this. Okay, so we have an open list and a closed list. And they actually need to be lists. I guess. Open needs to be initialized, mutable list of pairs, I guess. Int close looks like the same thing. I might have to change something here, so I didn't read this very closely. Put the starting node on the open. Okay. Open dot add 0 0. Okay. Oops. 0 0. Okay. You can leave it F at 0. I don't know about June. I don't know. I like doing this. It'd be cool to make it to 100 days straight. But this is also crowded out other programming stuff that I want to do. So those long days where it's like an hour, 2 hours, whatever. I don't know. There's just other stuff. So I don't know about June yet. I'm still thinking about it. What are you thinking? Gonna do it? What I worry about is me saying, oh, I'm going to do other kinds of programming, and then I don't. So it's been nice to have something to keep me in touch with it every day. While open.ini. I also thought about doing it in a different language, maybe Python, just something that is foreign to me that I should learn more about. I've definitely got Python code around work that it would be nice to be able to read it better. Whoa, that was cool. Just messing around with shortcuts. While the open list is not empty, find the node with the least F on the open list. Okay, what was F? Leave its F at 0. Okay, well, let's call this a triple then. And I guess it'll be 3. The last one will be a score. Okay. Initialize with F of 0. I already regret this being a triple. Let's see. Call a node. It's got a val I, val j. Draw from A is a cap. Well, I'll take a cap. I never win anything though, so I don't think I'll win. Call it F for now. I'd like to rename it to score eventually, if that's what it actually is. Dunes' t-shirt. That would be cool. Yeah, that's true. Although I wear hats a lot more often than I wear shirts. I wear my hats till they're falling apart. It's the MS Dev Show hat here that has seen better days. I've been wearing it for years. While there's anything in open, find the node with the least F. So val q equals pop q off the open list. How do we do that? Open dot remove. Can I give it a function? I'm tempted to just sort it. Dot sort by sort it by F, and then find the node with the least F. So we'll sort it, and then remove first. It's a list. Okay. Experimental? What? Here, I guess I could do linked list. And then it won't be experimental. Okay, so now we remove the first item. We sorted it ahead of time. Which is not... We'd be better off using heap or something here. But maybe this will be fine. Find the node with the least F on the list and call it Q. Okay. Pop Q off the open list. Okay. Generate Q's 8 successors. We don't have 8. And set their parents to Q. Generate Q's 8. How could it even have... Oh, okay, 8, because it's assuming you can go diagonal and stuff. Okay. So, if... Q's got an I and J, so if we look at our graph at Q.I and at Q.J, if it has a diagonal, then we should add it. Oh yeah, I was joking around when I said that. Yeah, I said it in a weird way. Yeah, I wear a lot of hats because I'm on Zoom a lot, even for work. Work from home, I'm always on camera, and so I wear hats so that my balding head doesn't blind anybody. And with the light right over my head, it makes it look like really light too, so it actually makes me look more bald than I am. I'm actually not very bald at all. I've got lovely, curly, thick locks. Said that for my wife's benefit. I don't know if she heard me. But if she did, she's probably getting a good chuckle right now because it's not so great anymore. So if we have a diagonal, then what? We add it to our successors. Successor list. Wow, that's weird. Node successor list. Nodes. So if you're a diagonal, then we can add you to our successor list. Dot add. And we will add a new node, and it will be Q.I, no, it'll be Q.I plus 1, Q.J plus 1, but because it's a diagonal here, we keep F the same, so we don't increment it. Okay. So otherwise, what we do is we add no, and this is not an else. Either way, we always add Q.I plus 1. Well, if I hate boundary checking, if Q.I is equal to graph.size minus 1. If you are greater than or equal to graph dot size minus 1, I should say less than, then we can add it. And this is not a diagonal move, so we just move 1 and it'll be Q.F plus 1. Phew. Okay, likewise, if q.j is less than graph at 0 dot size minus 1. Then let's go ahead and add q.i, q and j plus 1, and q.f. Now what I haven't done here is account for the situation where we have whatchamacallit. It makes me want to track something else here called, I don't know, state. Or type or kind of move, which will be an enum class, sure, called status direction maybe. We have right, down, and diagonal. Call this direction of direction. All right, so here it's a val. It doesn't change. So here for the first direction, we should not even count it. So do I want to say it's nullable, or do I just want to pick one, or maybe none? All right, we'll do none. And we go to the diagonal. Direction dot diagonal. Okay. Direction dot right. Direction dot down. That's it. Okay. We've generated the successors, and I didn't set any parents. All right. I guess I also want to know the parent. It's going to be a node. And it's nullable. Fine. All right. Here, I don't like nullables, but I really don't know what else to put there. All right. So your parent is Q. All of your parents are Q. Okay. So for each successor, successors for each, if it dot I equals graph dot size minus 1, and your j equals word2 dot length minus 1 because it's 0 based, then done. Stop search. What does stop search mean? If successor is the goal, stop search. Successor dot G. What the heck is G? What? Why? Whoa, I hate that phone so much. Sorry. Successors G equals Q's dot G. I thought we were doing F for distance, plus the distance between successor and Q. So in our case, I think it's basically just going to be the F value because we don't have weights. It's always just 1. So maybe we could do val min steps equals int dot max value So min steps equals whatever is smaller, min steps or it dot f. Okay. And it should be a var. Okay, so we found min steps. Now we stop the search. What is this .h? What is all this stuff that they're adding? This is the h distance from the goal to successor. Man, I wonder if Kotlin has a star built in. Algorithm. I should have read the algorithm all the way through before starting. Ugh. Just being lazy. For each successor, successor.g, successors.h is distance from the goal to successor. Blah blah. Successors.f equals successors.g plus .h. What does g mean here? Distance between the successor and q, which is always 1. Between successor and q. I don't get that. Let's find another article. Path equals blah. I don't even care about the path. Man, I should just do this myself. Like, this is annoying me. I don't need to care about most of these things. I'll probably regret this, but bye, Felicia. Okay. By a star. I will regret this. So. What do I want to do here? I only have 3 moves, right, down, and diagonal. Right, down, and diagonal. Our current equals, I'm going to keep this. I'm going to change that to distance. I will keep the direction. I don't think I care about parent because I'm going to do it recursively. Okay. So in the graph, you're going to tell me the current node. And it will be a node. All right, and do we need to know the distance? Nope. It will return the distance. Our stop condition is if current node, so we're going to rename to just current, dot I equals graph dot size minus 1, and current dot j is equal to graph at 0 dot size minus 1, and that's it. We're going to return 1. I think. All right, return 1. No min steps. We're just going to do this brute forcey and see how it goes. We can trim it up if we need to. Right. So our result equals, and basically we'll do one of our children. Whatever is best. So I guess I should say return whatever is the minimum between the 3 possible solutions, which are going right, minimum steps of I plus 1 j. I don't care about your distance. We'll store the direction though. Direction dot right. And let's just do it like this. And we'll if these guys here. Dot down. Steps. And if it's diagonal, it'll be both. Of current. If graph at current dot I at current dot j. We'll also add this. Do I want to check here or do I want to check it here? I don't know. I'll check it here. If it's a little bit redundant, but that's okay. If current.I plus 1 is less than graph dot size minus 1, then we can look at this one. Otherwise, we can look at this one. And the way we'll get the minimum is I'm just going to create a new data structure because I'm giving up on being efficient here. It's mutable list of nodes. Add. Oh, and it should be ints. Add and add. Return potential paths dot min, which whatever one of those is the least. Okay, now there's one other caveat, which is that this is a free move. Oh, but I'll call it diagonal, so we'll score it later. At the end, we won't count those. Okay, add a minimum steps, and minimum steps does need a direction, or does it? Yeah, it needs, oh man, this is getting nasty. It's like that. And like that. Oh boy. Minimum steps takes a graph and then a node, and the node is what has a direction, which is weird. So maybe I should call that a step or something instead of a node. It's just not a good name. And we do have a special case with direction none, which we'll do here in a minute. So then we'll need one more algorithm after this. We get this working that will basically score it. And so minimum steps, generate graphs was good. So generate graphs. We have to add a class of step and direction, which I'll put down below minimum steps. And we need one more function called score. Yeah, this is a problem though. This min is a problem. Crap. I guess what I can do here is basically if it's how do I know which one's really better? I think I'd basically add 0 there, add 1 if it's right or down. Alright, so that will recognize this as a freebie. Okay. Alright, and why? Should start with uppercase. Okay. You win again, IntelliJ. Let's keep it nice and conventional. Learn something new there. So score should take... oh, that means I need to return the nodes. Ugh. Alright, fine. You will take a list of steps called steps, and you'll basically return a score for it. Look out for insert plus delete combos. Okay, in either order should be fine. So, if I did like a windowed function, steps.window by size 2. Let's not do it that way. Let's just do a regular old for loop. For val I in steps dot indices. No val. And let's do size -1, which there's another way. I think it's until. It's gonna warn me about. Yep, until. So from 1 until steps dot size. All right, and if steps at I is equal to dot direction equals direction dot diagonal. No. No, it's fine actually. If it's diagonal or it's the that weird none step, then we could just continue. Else, if steps at I equals direction dot down and this one equals dot right. Let's keep a count here. All right. So we'll count plus plus. Maybe another way, better way to say this is to say, if it's down or it's right, then count plus plus. And we have a special situation here we have to watch out for, which is the current item equals down and the last one equals right. And it's minus minus. And then we have to worry about the case where we alternate. We don't want to double count it. So I think I might just be gnarly. And this is the last step. Last thing we do. So screw it. Steps I dot direction equals none. And that will prevent us from like double counting it in case the next one could have been a replacement. Is that good enough? So if we have basically like a right, down, down, right, this should let me use different characters. Right, down, right, down, and this should be a replace. This should be a replace. But I need to be careful that when I go right, down, say down, right, or no, there we go, right, down, right. I need to be careful to say you're a replace, but I don't want to double count you. So this is 2 steps. And I just need it to go down from 3 to 2, not from 3 to 1. Okay, so this will prevent that. It's kind of hacky. It's mutating state, which is gross. That's okay. So if we see this combination or the other one, equals right, and the one previous was down. What's the problem here, Kotlin? Cannot be applied to direction and a step. Fair enough. Alright, it's taken me 2 hours with cheating. This one's just beating me up. Steps at I dot direction equals none. Which means this now needs to be mutable because I'm doing something dirty. Alright, I'm not proud of that. So diagonals are free, which is probably, no, that's okay, that's good, because those are ones where we kept the original letter. Items where we did a replace count as 1, everything else just counts as 1. So at the end we return 1. And this function will be easier to test. So I'm less worried about this function as I am the traversal. All right. There we go. Steps is never used. So our final algorithm is val graph equals that. Steps equals we'll call this get minimum steps. Minimum steps. And we'll pass our graph. And we need to start with a node. Hey, what's up, the attacker? Hope you're having a good one. This has been a really tough problem. But I've learned about Meyers, the Meyers algorithm for diffing. And I got frustrated with A star and just ended up doing a less efficient algorithm because I look at more squares. And if this ends up being the problem, then I can dump in a standard A star algorithm. All right. Okay, that's implicit. All right, that's fine. Same here. All right. Hey, so I did not do that chair review. That was my buddy Alan on coding blocks, and I honestly can't answer that. So Alan is a bigger dude, and he sits in that chair, and he's got another one too, which I forget the name of, which also yeah, we share this channel, but like he is when I say bigger, I mean he's like made of muscle. He's like one giant ball of steel, super muscly, and yeah, I mean I should say too, yeah, I'm a bigger dude. I have a different chair, and I actually cannot remember what chair it is, but I can tell you, Alan works from home. We work together, and he is in that chair 8+ hours a day, and he's been sitting in it nonstop for probably 8 months now, every day 8 hours. And so I would say that chair is very strong. We've both been working from home for 6 years. So we got min distance, we get our steps, we got to pass a new node. Geez, but we call it steps. Step rather, 0, 0, the direction dot none. To seed this whole thing. And we got our steps, cool. Now we just need to return our score where we pass it the steps. Change steps of function score to int. What do you mean int? Score takes a list of steps. Oh, it's because this function doesn't return the right thing. Oh boy. So this needs to also have a mutable list of steps that's going to represent the path. Create class. So this is steps. I have no clue about out of country stuff. I'm very interested in out of country stuff. I've been working remote for years, so I definitely like the idea of work for either from another country or for something in another country. But man, I don't know. I think that there are some restrictions. So my guess is that the bigger companies, like the Googles and Fang and whatnot, they already have employees in other countries. So I would think that they would be fine with another one, but usually, they all have historically been not very remote friendly, so very unlikely to hire remotely. But that's all changing now. And I never go to an office. I don't have an office. I don't have a chair. I don't have a desk. My company doesn't have a building in my state. So it's like a 10-hour drive for me to get to an office, or an hour and a half flight. And there's a couple companies that are fully remote, like Elasticsearch, fully remote, Circle CI, fully remote. I think Datadog might be remote. Yeah, here you go. So, Datadog. I'm a big fan of Datadog. They sponsor the show. Full disclosure, they sponsor Coding Blocks. So bear in mind anything I say about them may be influenced by that, but their blog is amazing. Datadog, the engineering blog. So I think they'd be a great company to work for. They're very cloudy, so they would probably want someone with that kind of experience. So I don't know if that is interesting or not to you, but that's definitely a company that I'd be very interested in. They're probably going to be looking for like Kubernetes and Kafka experience. I know Elasticsearch is probably looking for Java info. Search remote dev. And I don't think they're based in the US either. Remote engineering. Let's see. This looks like we got some jobs listed on remote, or ZipRecruiter. Wait, that's not what I was looking for, but Elasticsearch, maybe if we just look at Elasticsearch careers. I wonder, there's got to be somebody who's written a blog post that says like the best remote companies to work for. But, JetBrains too. Let's see. Where are the jobs? My job, it just so happens that my company got acquired. My company was remote. Now the company we work for, Broadcom, does not. It's not that company likes remote work, but just my team already was distributed. So, So you can see all these say distributed. They do say Amer, so I don't know. They do have some others that are outside there. So I don't know what the deal is with that. Let's see, best remote companies. I've never heard of any of those. Oh, but I should specify programming. I've not heard of any of these. Is JetBrains remote? I think they're located in Prague. Remote. Oh, and they give us things to give away. Yeah. Oh, that's something else. JetBrains. They're going to be heavy Java shop though, so I don't know about C++. I'm just not in tune with that world really. Let's see. Find remote programming jobs. I felt like there was a site that was like specific for that. We work remotely. Yeah, it looks pretty cool. So I don't know anything about these companies, but it looks like an interesting way to find jobs. Let's see, programming. I do know wherever you're looking, you're gonna totally slay it. So the kind of challenges you're doing every day are exactly the kind of stuff that they're gonna be asking for. I think. Whoa. Score steps. Man, this one is challenging my stamina. 2 hours in and still have a ways to go. Wow. I think I think at this point I might be willing to cheat. I feel like this is a good solution. I feel like this does it. The runtime is not fantastic, but I think it's within acceptable bounds. But I'm just kind of tired. I feel like I learned a lot, so I think I'm just gonna cheat. I don't want to continue. I don't want to change my my get minimum steps algorithm to return a list instead. I mean, I guess it wouldn't be terrible, but I just don't want to deal with it. So I'm just gonna cheat. Edit distance Kotlin. Let's see if I can even cheat. Leak code. See this. If I win the hat, I'm gonna feel super guilty. There's the other problem I cheated on too. Four different solutions with recursion. Maybe we'll look at that one. Java. Anybody do Kotlin? All right, let's look at these fellas. Oh my gosh, look at this. Wow. Approach 1, simple recursion. Min distance. I don't know what ED is. Something Euclidean distance maybe. Takes word. If I is equal to the word 1 length. Okay, return J2 length minus 1, so it counts down. Okay. Top down DP. I'm definitely concerned to not see anybody else solving like I was solving it, so maybe my approach wouldn't have worked. Maybe there's something I didn't know about it. Bottoms up DP. Okay. Bottoms up DP with space optimization. Yeah, so I'm going to count today as a fail. But then I'm just going to paste this thing in. I definitely wasn't expecting a hard, and that kind of makes me not want to do June. So I just don't want to spend 2 hours plus. I mean, it'd be good. Like, I definitely learned some things today, which is good. You know, that's what I was wanting to do. But, oops, I forgot to copy that. Yeah, I just don't know if I want to commit another month of doing these things. So figure on average 1 hour a day. So 30 hours. Ooh. So there, it converted to Kotlin for me. Let's see how it did. All right, let's see how this did. I'll put a big note in here saying that I cheated. I should have not lost the one too. All right. Gave up, read the descriptions, copied from description. And if I win the hat, I will, I don't know, donate the hat or something. I'll send it to you, Abdul. I'm sure it's not going to happen. So I'm going to have to look at this closer. But I'm just kind of tired. Just not feeling it. Hey, there we go. Great. I would have felt bad if I was at the top. Wow, the best people did. Jeez. Yeah, I guess I'm just burnt out because even looking at this, I'm like, I don't even, my brain just doesn't want to read it. But the Meyers algorithm looked really interesting. So I'm going to add this problem to problems that I want to do again. Add distance. Yeah. Well, I mean, I copied and pasted the code and let Kotlin convert it for me. So I've got a folder here, I think called something like problems to do again. So I'll add that there. And I don't even know how to use my bookmarks. So the other item that I bookmarked before was this one. Oh, uncrossed lines. Remember this one? So this is the other one I cheated on. Okay, so there's two that I cheated on in the last 2 months. I didn't cheat at all last month. This month definitely did. Yay, completed a challenge, 200 coins. I hate cheating on the last one, but oh well. If we look at June, I wonder if it says like these problems are so easy anybody could do them. Submissions only. So for May, they definitely said these are easy enough for anybody to do them. I did not see that on June. Let's see. If we go back to Explore. I don't know. I could have sworn I read that, but maybe I imagined it. I don't even know where to find it. I can Google for it. May Leak Code Challenge. So easy. It's going to be so easy. Anybody could do it. Alright, I guess I made that up. Alright, whatever. I give up. Done. Dunzo. Challenge completed. Learned some things about the two problems I had. I also learned about Meyers algorithm. So I probably should add that to my list. That was the one with the longest. I cheated on that one too. So I cheated on 3 this month. So if you come in here, there was one with the circular array. It wasn't the first week. Let's see. Nope. What was possible by partition? No, that one was okay. There it is. Maximum sum circular subarray. That was the one that had the really cool deal where you basically remove the items that were the least. Okay, beginner friendly. Hey, thanks for finding that. Yeah, so beginner friendly, I definitely don't think that last one was beginner friendly. But I don't know. I definitely didn't run across that. I was aware of diff algorithms, so I guess I should say I did run across that at some point at school. I'm pretty sure I didn't ever have to program it or anything. I'm gonna mark this one for do again. I was also kind of tempted, so if I don't do the June leak code, then I'm kind of tempted to go through April and May again and just see how I do on those now that I've done them once, just for fun. I should be able to blast through them a lot quicker than the first time around. I thought it might be a good way of kind of solidifying those ones I had problems with. So, give that a shot. Alright, I'm going to get out of here. Thank you so much for hanging out. Hope you guys have a good one, and yay, welcome to June. Alright, take it easy.